In 1970, Soviet scientists started drilling straight down into the earth. Their target? 15 kilometers, deeper than the Mariana Trench, deeper than any human had ever reached. 20 years later, at 12 kilometers, they stopped. Not because the funding ran out, not because the drill broke, because the rock at the bottom was so hot it had turned into something that wasn't rock anymore. It was flowing, closing the hole behind the drill like a wound healing itself. And the things they pulled up from that depth, water that shouldn't exist, fossils 2 billion years old, gas with no explanation, forced geologists to throw out models they'd been teaching for 60 years. This is the story of the deepest hole ever made by human hands, and what it found down there that nobody expected. If you're into this, subscribe and drop a like. It helps more than you think. Let's go. On the morning of May 24th, 1970, a man named David Guberman stood on a patch of frozen tundra 16 kilometers from the Norwegian border and watched a drill bit touch granite for the first time. The air smelled of diesel and iron. The ground beneath his boots was Precambrian rock, 2.5 billion years old, older than anything that had ever drawn breath on this planet. The Uralmesh 4 E-rig above him groaned and shuddered, its steel frame vibrating against the Arctic sky. Guberman was not a driller. He was a geologist, the chief scientist of a project so ambitious that even the Ministry of Geology had hesitated before approving it. The target was 15,000 meters, straight down. No angle, no deviation, no compromise. 15 kilometers. That is roughly the altitude at which a commercial jet crosses the Atlantic. Except the direction was reversed, and instead of thin air, every meter downward meant denser rock, higher pressure, and rising heat. No human had ever reached that depth. No machine had been tested for it. The plan existed on paper, in equations, in theoretical models that Soviet geophysicists had spent a decade refining. Whether those models bore any resemblance to reality, that was precisely what Guberman intended to find out. The Kola Peninsula was not a random choice. This wedge of Arctic land between Finland and the Barents Sea sits atop the Baltic Shield, one of the most ancient and stable geological formations on Earth. The rock here has not been disturbed by tectonic folding or volcanic intrusion for over 1 billion years, a geological stillness almost unheard of on a planet defined by motion. It is, in geological terms, a window, a place where the deep crust lies closer to the surface than almost anywhere else on the continent. If you wanted to drill into the planet's interior, this was the place to start. Around the rig, the landscape was treeless and flat. Snow lingered into June. Winter temperatures on the Kola Peninsula dropped below minus 30 degrees Celsius, cold enough to crack exposed steel. The nearest town, Zapolyarny, was a mining settlement of a few thousand people, nickel workers mostly, and their families. The research station that would grow around the borehole did not yet exist. There were no laboratories, no housing blocks, no canteen. Just the rig, a team of engineers, and a hole that had not yet been drilled. Guberman had pushed for this project for years. He was one of the initiators of the Soviet Superdeep Wells program, alongside Yevgeny Kozlovsky, the USSR Minister of Geology. The idea was straightforward in principle and staggering in ambition. Drill deeper than anyone had ever gone. Recover intact rock cores from every kilometer
and compare what the drill found with what seismic surveys said should be there. The textbooks described Earth's upper crust as a layer cake, granite on top, basalt beneath, separated by a clean boundary called the Conrad discontinuity. Every geology student learned it. Every seismic model depended on it. Guberman suspected it might be wrong. The drill turned. The first meter of granite yielded, then the second. The chips came up gray and streaked with feldspar, exactly as predicted. And for the next 9 years, almost everything would go according to plan. The surprises, the ones that would force geologists to rewrite entire chapters of their textbooks, were waiting below 10,000 meters. They were patient. They had been there for 2 billion years. What waited for them at the bottom would take 2 decades to reach, and would contradict almost everything they believed about the planet beneath their feet. The Cold War was not only fought in orbit. While the world tracked satellites and lunar modules crossing the sky, a quieter competition was unfolding in the opposite direction, straight into the Earth. In 1957, the same year the Soviet Union launched Sputnik, a group of American scientists proposed what they called Project Mohole. The concept was elegant. Instead of drilling through tens of kilometers of continental rock, they would punch through the ocean floor, where the crust is only 5 to 7 kilometers thick, and reach the Mohorovicic discontinuity, the boundary between the crust and the mantle. The name was half geology, half joke. The American Miscellaneous Society, an informal group of geoscientists, chose a site near Guadalupe Island off the Pacific coast of Mexico and began drilling in 1961. They reached 183 meters into the seafloor. Under 3,566 meters of open ocean. Then Congress cut the funding. By 1966, Project Mohole was dead. $100 million endeavor that had barely scratched the seabed. The official reason was cost overruns. The unofficial reason was simpler. The moon was more photogenic. Rockets made headlines. Drill bits did not. Moscow was watching. The Soviet geological establishment, centrally funded, insulated from budget cycles, and answerable only to the Politburo, saw an opening. Where the Americans had tried to cheat the crust by going through the ocean, the Soviets chose a different strategy entirely. They would drill through solid continental rock, starting from one of the most geologically stable surfaces on the planet. The Baltic Shield's granite had been sitting undisturbed since the Archean Eon. No subduction, no volcanic intrusion, no tectonic folding. It was, in a sense, the simplest rock on Earth. Simple to understand, not simple to penetrate. The project's scientific mandate covered 4 domains: the deep structure of the Baltic Shield, the nature of seismic discontinuities in the continental crust, the thermal regime at extreme depths, and the physical and chemical composition of rocks that no human had ever seen. 16 scientific research laboratories were attached to the project. At its peak, up to 3,000 specialists, geologists, geophysicists, petrologists, engineers, drilling crews, worked on or around the borehole simultaneously. The Kola Superdeep was not a well. It was a subterranean observatory, an inverted telescope pointed at the interior of the planet. The Americans had aimed for the mantle and quit at 183 meters. the Soviets aimed for 15 kilometers and meant every digit. The question was not whether they had the ambition. The question was whether any material on Earth, steel, tungsten carbide, diamond, could survive the conditions that waited below the first 5 kilometers. The answer, as the engineers would discover, was more complicated than anyone had planned for. The Americans had tried from the ocean floor and failed. The Soviets chose solid granite. The question was whether any drill on Earth could survive what waited below the first 5 kilometers. Most people picture a drill as something that spins, a rotating column of steel boring its way through material by sheer force and friction. That is how oil wells work. That is how construction rigs work. That is not how you drill 12 kilometers into Precambrian granite. At those depths, a rotating drill string would twist under its own weight. The torque required to spin a column of steel taller than Mount Fuji would shatter the shaft long before the bit touched new rock. Soviet engineers solved this with a technique called turbo drilling. The drill string stayed still, only the bit moved. High-pressure drilling fluid, a dense, chemically treated mud, was pumped down through the hollow interior of the pipe at enormous velocity. At the very bottom, this fluid struck a turbine housing mounted just above the cutting head, and the turbine spun the bit at several hundred revolutions per minute while the rest of the column remained stationary. It was counterintuitive. It was brilliant. It meant that the only component under rotational stress was the final few meters of the assembly: the turbine, the bit, and the stabilizer ring. The remaining 12 kilometers of pipe hung motionless in the hole, a hollow column that carried fluid down and core samples up. Retrieving a single core sample from the bottom of the borehole took up to 18 hours. 9 hours to pull the assembly up, extract the rock cylinder, and 9 hours to lower everything back down. One sample, one day. In 1974, after the first 4 years of drilling, the original Uvalmash 4E was dismantled and replaced. In its place rose the Uvalmash 15,000, a purpose-built super deep drilling rig, one of the most powerful ever constructed. Its derrick towered over the tundra like a steel cathedral. The designation was not subtle. The number referred to the target depth in meters: 15,000. The machine was engineered to reach a place that existed at that point only in theory. Progress was measured in meters per day, sometimes meters per week. The drill bit, tungsten carbide teeth on a steel body, lasted between 40 and 200 hours before it dulled against the granite and had to be replaced. Each replacement meant the entire drill string had to be pulled to the surface, the bit swapped, and the string lowered again. At 8 kilometers, this round trip took the better part of 2 days. At 10 kilometers, nearly 3. The deeper the hole, the slower the rhythm. On June 6, 1979, the drill passed 9,583 meters and crossed a line that no human-made object had crossed before. The previous record had belonged to the Bertha Rogers hole in Washita County, Oklahoma, an exploratory gas well that had reached its limit when it struck molten sulfur. The Bertha Rogers project lasted 2 years. Kola had already been running for 9. The record barely made Western newspapers. In Moscow, it was noted with quiet satisfaction and filed alongside the other trophies of Soviet engineering. By 1983, the borehole had passed 12,000 meters. At that depth, the diameter of the shaft had narrowed to 23 centimeters. 23 centimeters, roughly the width of a dinner plate. Picture it, a tube the width of a plate dropping straight down through solid rock for a distance greater than the depth of the Mariana Trench. If you could somehow look down into it, you would see nothing. Light does not travel 12 kilometers through a 9-inch pipe. Sound barely does. The only information that came back from the bottom arrived in the form of rock cores, temperature readings, and the chemical composition of drilling mud. 9 inches wide, 12 kilometers deep. The engineering was extraordinary. The execution was flawless. What the drill found, however, was something no engineer had anticipated, because the textbooks were wrong. For most of the 20th century, geologists believed that the continental crust had a layered structure, granite on top, basalt beneath. The boundary between these two layers was called the Conrad discontinuity, named after the Austrian seismologist Victor Conrad, who proposed it in 1925, based on the behavior of seismic waves. When an earthquake sends shock waves through the planet, those waves speed up as they pass from less dense material to more dense material. At a depth of roughly 7 kilometers beneath most continents, seismographs consistently recorded a sharp acceleration, a velocity jump that could only mean one thing. The waves had crossed from granite into basalt. This was not a hypothesis. It was a measured fact. It appeared in every geology textbook printed between 1930 and 1990. The drill reached 7 kilometers. There was no basalt. There was no basalt at 8 kilometers. There was no basalt at 9. At 10, 11, 12 kilometers, through every centimeter of core sample pulled from the borehole over a span of 13 years, the rock remained granitic. The Conrad discontinuity, the clean horizontal boundary that generations of geologists had drawn on their cross-section diagrams, did not exist. Not here. Possibly not anywhere on continental crust. What the drill did find was a transition, not between two different rock types, but between two different states of the same rock. Above 7 kilometers, the granite was igneous, crystallized from molten magma, hard, predictable, its mineral grains locked in rigid formation. Below 7 kilometers, the granite was metamorphic, the same chemical composition, but transformed by heat and pressure into something denser, with realigned crystal structures and compressed mineral boundaries. The seismic waves had not been responding to a change in material. They had been responding to a change in the material's internal architecture. For 60 years, geophysicists had been reading the signal correctly and interpreting it wrong. That alone would have been enough to overturn a century of crustal modeling. It wasn't the only surprise. At depths between 6 and 12 kilometers, the drill cores came up wet. Not damp, wet. Liquid water, highly mineralized, filled fractures and pore spaces in rock that was supposed to be bone dry. At those depths, the overburden pressure exceeds 1,000 atmospheres, the equivalent of stacking a column of steel 8 kilometers high on every square centimeter of surface. Conventional geology held that no open space could survive such compression. The fractures should have been sealed shut. The water should not have been there. It was there, and it was not a trickle. The volume of fluid in those deep fractures suggested a connected hydrological system. Not surface water seeping down, but water that had been trapped in the rock matrix since the crust solidified, circulating through microscopic channels under immense pressure. Some of it may have been billions of years old, imprisoned since the Baltic Shield first cooled from magma. The water was not alone. Throughout the length of the borehole, from the first kilometer to the last, gases bubbled up through the drilling mud. Hydrogen, significant quantities of it, rose continuously from the deep sections. Helium, nitrogen, and carbon dioxide accompanied it in varying concentrations. The hydrogen was particularly puzzling. On the surface, free hydrogen is rare. It bonds readily with oxygen and escapes the atmosphere. Beneath the crust, it was pouring upward in steady streams. The source was unclear. Some researchers suggested radiolysis, the splitting of water molecules by natural radiation from uranium and thorium in the rock. Others pointed to serpentinization, a chemical reaction between water and iron-rich minerals that releases hydrogen as a byproduct. Neither explanation fully accounted for the volume. The rock was wrong, the water was impossible, the gas had no definitive source. Every model of the Earth's crust had assumed that granite gives way to basalt. Kola proved it doesn't, and in the process, opened a question that geologists are still debating. If the Conrad discontinuity is not a real boundary, how much of what we think we know about the deep crust is based on misread seismic data? The most unsettling discovery, however, wasn't geological. It was biological. The core sample arrived at the surface looking like every other. A cylinder of dense, dark granite, warm to the touch from the heat of 6.5 kilometers of overburden. A technician in the on-site laboratory split it along its bedding plane, mounted a thin section on a glass slide, and slid it under a petrographic microscope. What he saw made no sense. Embedded in the rock matrix, sealed inside pockets of organic carbon and nitrogen compounds, were fossils. Not impressions, not mineral traces, intact cellular structures. 24 distinct species of single-celled organisms preserved in the kind of detail that paleontologists associate with amber, not with crustal granite under 600 atmospheres of pressure. The depth was 6.7 kilometers, 22,000 feet below the surface. The age of the host rock was 2 billion years. 2 billion years ago, Earth was a different planet. The atmosphere contained almost no free oxygen. The oceans were green with dissolved iron. There were no plants, no fungi, no animals of any kind. Only prokaryotic microbes drifting through chemical seas under a sky tinted orange by methane haze. The fossils in the Kola core belonged to that world. They were marine plankton, organisms that had lived in shallow water, died, sunk into sediment, and been buried under kilometers of accumulating rock over geological timescales that dwarf the entire history of complex life. The dinosaurs came and went, Pangaea assembled and broke apart, ice ages advanced and retreated dozens of times, and these cells remained, locked in stone, at temperatures exceeding 150 degrees Celsius. The organic compounds surrounding them, carbon and nitrogen in molecular configurations that do not form abiotically at those temperatures, appeared to have acted as a chemical shield. They had insulated the fossils from the very conditions that should have destroyed them. This was not a known preservation mechanism. It had never been observed in surface geology, where organic matter breaks down rapidly under heat. At depth, under pressure, the chemistry had apparently reversed. The carbon matrix had hardened rather than decomposed, creating microscopic sarcophagi that held their contents intact for 2 billion years. The implications were immediate and uncomfortable. If intact biological material could survive at 7 kilometers in 150-degree rock under pressures that should have crushed every pore space shut, then the assumed depth limit for life on Earth was wrong. At the time of the discovery, mainstream biology placed that limit at a few hundred meters, the point below which temperatures, pressures, and the absence of sunlight were thought to make biological activity impossible. Kola's microfossils didn't just push that boundary deeper, they obliterated it. There was more. The carbon dioxide that had been bubbling up through the drilling mud throughout the project, one of the gases dismissed as a minor curiosity, showed isotopic signatures consistent with biological metabolism. Not ancient metabolism, active metabolism. Something down there was alive. Not the fossils themselves, but microorganisms in the deep rock matrix that were processing carbon compounds and releasing CO2 as a metabolic byproduct. In the 1970s, this was heretical. The idea that living organisms could inhabit rock kilometers below the surface, without sunlight, without oxygen, without any connection to the biosphere above, had no theoretical framework. The term deep biosphere would not enter scientific vocabulary for another 2 decades. Kola was ahead of the language. The drill had found life where every model said life could not exist. Preserved death that was 2 billion years old, and living processes that were happening in real time, side by side, in the same column of rock. They had been down there for 2 billion years. The fossils, the microbes, the water, waiting for someone to look. The fossils proved that life could survive where nothing should survive. Except the question was no longer what the drill could find. Below 10,000 meters, the Earth stopped behaving like rock. The geothermal gradient, the rate at which temperature rises with depth, was supposed to be predictable. Soviet geophysicists had calculated it before the first meter was drilled, roughly 30 degrees Celsius per kilometer in the upper crust, tapering to 25 degrees deeper down. At 15 kilometers, the target depth, models predicted a bottom hole temperature of approximately 100 degrees Celsius. Manageable, within the operating tolerance of existing drill bits and lubricants. The entire engineering plan, the Euromash 15000's design parameters, the composition of the drilling mud, the metallurgy of the turbine housings, was built around that number. The number was wrong. By the time the drill passed 10,000 meters, the temperature had already exceeded 140 degrees. At 11,000, it crossed 160. At 12,262 meters, the final depth, thermocouples registered 180 degrees Celsius, 356 degrees Fahrenheit, nearly twice the predicted value. The geothermal gradient in the Kola borehole was not 30 degrees per kilometer. It was closer to 45 in the deeper sections, a rate that no existing thermal model of the Baltic Shield had anticipated. 180 degrees is the temperature inside a superheated steam line in a power plant. It is the temperature at which surgical instruments are sterilized in an autoclave. It is not the temperature at which steel drill bits are expected to function, drilling fluid is expected to circulate, or rock is expected to remain solid. Past the 14,800 foot mark, 4,511 meters, the porosity and permeability of the granite had begun to shift. The rock was riddled with microfractures, saturated with pressurized fluid, and increasingly plastic. At the deepest sections, the granite no longer fractured cleanly under the drill. It deformed. It flowed. It behaved less like stone and more like warm wax, yielding to pressure, then slowly closing behind the drill bit, narrowing the borehole millimeter by millimeter as the weight of 12 kilometers of overburden squeezed the shaft shut. The engineers fought this with drilling mud, a heavy, chemically treated fluid pumped down to cool the bit, carry rock cuttings to the surface, and exert hydrostatic pressure against the borehole walls to keep them from collapsing. At 12 kilometers, the mud itself began to break down. Its chemical stabilizers degraded in the heat. Its viscosity dropped. The cooling effect diminished. The bit ground against semi-plastic rock in a bath of fluid that was slowly losing every property it had been designed to provide. Then the drill string broke. Not a crack. Not a fracture at a joint. A 5-kilometer section of the assembly, 5,000 meters of continuous steel pipe, sheared off cleanly and fell to the bottom of the borehole. The failure was instantaneous and catastrophic. The section could not be retrieved. There was no tool capable of fishing 5 kilometers of steel out of a 9-inch shaft filled with pressurized mud at 170 degrees. The drilling team sealed the lost section, backed up to a branching point several thousand meters higher, and started again. This was not the only time it happened. The borehole that reached 12,262 meters was not a single straight shaft. It was a tree, a central trunk with multiple dead-end branches, each representing a failed attempt that had been abandoned due to equipment failure, stuck pipe, or unmanageable rock conditions. The final depth was reached on only one branch. The others remain sealed in the rock, their drill bits and pipe sections entombed in plastic granite that has long since closed around them. By 1992, the project had exhausted its engineering options. The rock at the bottom was too hot, too plastic, and too unpredictable for any existing technology. The target of 15,000 meters, the number stamped on the Euromesh 15,000's nameplate, the number written into the original 1969 project charter, remained 2,738 meters away. Close enough to calculate, too deep to reach. The drill had hit a wall, except the wall was not solid. It was flowing. The planet was pushing back. The deeper they went, the more the Earth resisted, as if geology itself had a threshold it refused to let humans cross. The question was no longer how deep the drill could go. It was what the drill had already revealed about the planet we thought we understood. Earth's radius is 6,371 kilometers. The Kola borehole reached just over 12. That is 0.19%, less than 2/1000 of the distance from the surface to the center. The deepest hole ever drilled by human beings penetrated less than 1/5 of 1% of the planet it was drilled into. An apple. The skin of an apple. That thin, waxy layer you bite through without thinking represents roughly 1 to 2% of the fruit's total radius. The Kola borehole, scaled to an apple, would not break through the skin. It would not reach the flesh. It would be a needle mark, invisible to the naked eye, pressed into the outermost molecules of the peel. Continental crust averages 35 kilometers in thickness. The drill reached just over a third of the way through. Below the crust lies the mantle, 2,900 kilometers of rock, so hot that it convects in slow planetary currents, carrying tectonic plates on its surface like scum on simmering water. Below the mantle, the outer core, 2,200 kilometers of liquid iron at temperatures exceeding 4,000 degrees. Then the inner core, a solid sphere of iron and nickel, roughly the size of the Moon, compressed to a density of 13 grams per cubic centimeter by the weight of everything above it. The Kola drill did not come close to any of this. It didn't even finish the crust. Meanwhile, in the opposite direction, humanity has been rather more successful. Voyager 1, launched in 1977, 7 years after Kola's first drill bit touched granite, has traveled more than 24 billion kilometers from Earth. It has crossed the heliopause and entered interstellar space. The ratio between the farthest we have reached outward and the farthest we have reached inward is roughly 2 million to 1. We have explored the solar system 2 million times more thoroughly than we have explored the rock beneath our own feet. 12 people have walked on the surface of the Moon. 6 robotic vehicles have driven on Mars. We have photographed the methane lakes of Titan, the nitrogen glaciers of Pluto, and the hydrogen storms of Jupiter from distances that would take light hours to cross. The number of human beings who have directly observed the bottom of the Kola Superdeep Borehole is 0. It is too narrow for any camera, too deep for any probe, and too hot for any instrument that does not travel in a bath of refrigerated drilling fluid. The deepest point our species has ever reached on its own planet is known only through the proxy of rock cores and temperature sensors. Indirectly, abstractly. The way we know distant galaxies. By the data they send us. Never by touch. The asymmetry is specific to geology, and to geology alone. We have mapped the gravitational field of a comet 400 million kilometers away with higher resolution than we have mapped the thermal gradient 30 kilometers beneath Central Europe. We can predict the surface temperature of an exoplanet orbiting a star in the constellation Cygnus, and we cannot say with certainty what rock type lies 20 kilometers below Berlin. The interior of our planet remains, in practical terms, less explored than the surface of Mercury. The Kola project proved it was possible to reach the deep crust, and simultaneously proved how little of the deep crust we had actually reached. We mapped the far side of the Moon before we understood what lay 7 kilometers below the surface. And when the Kola data started circulating, fragmentary, classified, extraordinary, it didn't just challenge geology, it spawned one of the strangest urban legends of the 20th century. Sometime in late 1989, the exact date is uncertain because the story mutated each time it crossed the border. A television broadcast in the United States made an extraordinary claim. Soviet scientists, the report said, had drilled a borehole 14.4 kilometers into the earth. At that depth, the drill had broken through into a vast hollow cavity, an underground void where temperatures exceeded 2,000 degrees. The scientists lowered heat-resistant microphones into the opening. What came back through the speakers was the sound of screaming. Thousands of human voices wailing in agony, rising from deep beneath the crust. The broadcast aired on the Trinity Broadcasting Network, a Christian television platform based in Southern California. The segment was titled Scientists Discover Hell. It included no named sources, no verifiable coordinates, and no footage. Only a grainy audio clip of what sounded like a chorus of anguished voices echoing through a stone chamber. The clip was vivid, disturbing, and entirely fabricated. Investigators later identified the audio. It was a manipulated loop from a 1972 Italian horror film called Barren Blood, directed by Mario Bava. The screams had been extracted from the film's soundtrack, slowed down, layered over themselves, and processed through reverb to simulate the acoustics of a deep shaft. The technical effort was minimal. The effect was extraordinary. Within weeks, the story had escaped television and entered the evangelical information ecosystem. The path of transmission was remarkable in its own right. A Norwegian schoolteacher visiting California heard the TBN broadcast and brought the story home. He mailed a written version to a Christian magazine in Finland. The Finnish magazine published it, not as an article, but as a reader's letter. From there, it was picked up by a missionary's newsletter aimed at Finnish-speaking communities abroad. The newsletter circulated through Scandinavian church networks and eventually returned to the United States, where American evangelists cited it as evidence sourced from a respected Finnish scientific journal. The loop was closed. A story that had been invented in a California television studio had traveled through Norway, Finland, and back to the United States, acquiring credibility at each border crossing. By the time it re-entered American media, it appeared to have independent European confirmation. It did not. Every version traced back to the same broadcast, the same anonymous source, the same spliced film audio. The hoax claimed the borehole was 14.4 kilometers deep, 2 kilometers deeper than the actual project ever reached. It claimed temperatures of 2,000 degrees, more than 10 times the real figure. It claimed a hollow cavity in a region of solid, compressed granite where no cavity could physically exist. Every specific detail in the story was wrong by an order of magnitude. This did not slow its spread. What made the well-to-hell legend resilient was not its plausibility. It was the secrecy surrounding the real project. During the Soviet era, the Kola Superdeep Borehole was a restricted facility. Publications about its findings appeared primarily in Soviet geological journals, most of them in Russian, few of them translated. Western scientists had limited access to the data. The general public had none. Into that information vacuum, a genuine deep earth drilling project, producing genuinely extraordinary results behind a wall of Cold War classification, the legend found fertile ground. The truth was inaccessible. The lie was available. People chose what they could reach. The real discoveries, the missing basalt, the deep water, the ancient microfossils, the rock that behaved like plastic, were stranger and more significant than anything the hoax described. The planet's actual interior was more alien than the fictional hell beneath it. Except the real findings required geological literacy to appreciate, while the screaming required only speakers. The hoax faded, the borehole didn't. Even as the Soviet Union collapsed around it, the question remained, could anyone go deeper? In 1987, while Soviet engineers were still fighting plastic rock on the Kola Peninsula, a second super-deep drilling project began in Bavaria. The German Continental Deep Drilling Program, Kontinentales Tiefbohrprogramm, or KTB, sank a borehole into the crystalline basement of Central Europe near the town of Windischeschenbach. The Germans had newer technology, better funding models, and the benefit of studying Kola's published data before designing their own approach. They reached 9,101 meters. Then the temperature hit 260 degrees Celsius, 500 degrees Fahrenheit, and the project stopped. The rock at the bottom of the KTB borehole was gneiss, a metamorphic formation similar to what Kola had encountered. The conclusion was the same. The Earth gets hotter faster than models predict, and at a certain depth, the heat winds.
The KTB ran from 1987 to 1995, the same year the Kola project officially closed. 2 boreholes, 2 countries, 2 independent data sets, and the same result. The continental crust is hotter, wetter, and more chemically active than any surface-based measurement had suggested. Seismic surveys are useful approximations. They are not maps. For nearly 3 decades after that, the field went quiet. Deep scientific drilling continued in ocean basins. The International Ocean Discovery Program operates a fleet of research vessels that routinely core through the thin oceanic crust. But on land, the super deep frontier remained frozen at Kola's record. Then China entered the race. In 2023, Chinese engineers began drilling the Shenditak 1 borehole in the Tarim Basin, Xinjiang, one of the oldest and most geologically complex sedimentary basins on Earth. By March 2024, the drill had reached 10,000 meters, passing through 10 distinct rock formations spanning 145 million years of geological history. The Tarim borehole is not a pure science project. It combines scientific exploration with hydrocarbon surveying. Oil and gas companies are co-funding the effort in exchange for subsurface data. The model is pragmatic. It may also be sustainable in a way that Cold War prestige projects were not. Meanwhile, a different approach to deep drilling is emerging from engineering laboratories in the United States and Europe. The fundamental problem with mechanical drilling, the reason the Kola project stalled and the KTB project stopped, is that rotating metal bits cannot survive temperatures above 200 degrees for extended periods. The rock softens, the bit dulls, the lubricant degrades, and the entire system fails. Several teams are now developing alternatives that bypass the drill bit entirely. Plasma pulse drilling uses rapid electrical discharges to fracture rock thermally without physical contact. Millimeter wave drilling fires concentrated microwave energy at the rock face, melting it in place. Gyrotron-assisted boring, developed partly from fusion reactor technology, generates beams of electromagnetic energy powerful enough to vaporize granite at temperatures exceeding 3,000 degrees. These systems have no moving parts at the cutting face. They do not wear out. If the technology matures, the implications extend well beyond geology. At 10 kilometers or more, rock temperatures on every continent exceed 300 degrees Celsius, hot enough to generate electricity through closed-loop geothermal systems without volcanic activity, without tectonic hotspots, and without fossil fuels. A single deep geothermal well drawing heat from rock that has been accumulating thermal energy for billions of years could power a small city indefinitely. The heat is already there. The only barrier is reaching it. Seismologists have proposed another application: deep monitoring wells drilled near active fault zones. Sensors placed at 10 kilometers along the San Andreas Fault, the Anatolian Fault, or the subduction zones of a Pacific rim could measure stress accumulation in the rock in real time, detecting the slow buildup of elastic strain that precedes a rupture. Current earthquake prediction models rely on surface instruments and statistical inference. Deep boreholes could provide direct mechanical data from the zone where earthquakes originate. Some models suggest this could extend warning times from seconds to hours, potentially 24 to 72 hours of advance notice before a major seismic event. The technology is closer than it has ever been. The planet hasn't changed. Somewhere between the two lies the answer to whether we'll ever reach the mantle, or whether 12 kilometers will remain the permanent ceiling of human exploration inward. In 2007, the Russian Academy of Sciences formally dissolved the scientific team attached to the Kola Superdeep Borehole. The remaining equipment, instruments, core storage facilities, computing hardware that had been state-of-the-art in the 1980s was transferred to a private company. The company was liquidated 1 year later, in 2008, for unprofitability. There was nothing left to profit from. The rig had been dismantled. The laboratories had been stripped. The housing blocks that once sheltered 3,000 specialists stood empty, their windows dark, their corridors open to the wind. Today the site is a ruin. Rotting timber, collapsed roof panels, sheets of scrap metal half buried in permafrost and brush. The only marker of the deepest point our species has ever reached on its own planet is a metal cap bolted to a concrete slab at ground level. It is round, it is rusted, it is roughly the width of a manhole cover's bolt ring. Beneath it, if the shaft has not yet collapsed under geological pressure, lies a column of empty space that extends downward for a distance greater than the height of 14 Mount Everests stacked summit to base. A vertical wound in the crust, drilled 1 meter at a time over 24 years by teams of engineers who never saw the bottom of what they built. David Guberman spent more than 40 years on the project, from the first planning documents in the 1960s to the final administrative meetings in the 2000s. He was not a man who gave up easily. He outlasted the rig, the funding, the country that had built it. When the Soviet Union dissolved in 1991, the borehole was already 12 kilometers deep and the budget was already gone. Guberman continued. He wrote proposals, he sought partnerships, he published papers in journals that fewer and fewer people read. The hole was there, the data was extraordinary. The world had moved on. The borehole itself is not static. At 12 kilometers, the rock is under continuous compressive stress. The shaft is slowly narrowing. Plastic granite creeping inward, millimeter by millimeter, reclaiming the space that was carved out of it. Within decades, possibly sooner, the deepest section will seal itself entirely. The rock will close. The water will fill the remaining voids. The microfossils will return to darkness. And the only physical trace of the deepest human-made point on Earth will be a rusted circle of steel on a concrete pad in the Kola tundra. Surrounded by the kind of silence that only exists in places where something enormous once happened and stopped. The Earth is already closing the wound.